Stars, they are the furnaces of the universe, the cauldron where new elements are created. But stars die, and when they do, act like ticking time bombs. Let me explain this rather confusing statement by talking about the life cycle of stars. A star is a massive hot ball of gas, in which lighter elements like hydrogen are smushed together by extremely strong forces of gravity and high temperatures to form new elements like helium, releasing energy in the process. These heavier elements too can combine with their counterparts to form even heavier elements, releasing energy as well. This process, called nuclear fusion, releases energy and light, and that's why stars shine. This also produces a force which counteracts the force of gravity, keeping the star inflated in a perfect state of balance. However, this cannot continue forever. At a certain point, some elements are just too heavy and stable to be combined together to form a new element. Some lighter stars, which exert less gravitational pressure, can't fuse carbon, while heavier stars, which push harder, can't fuse iron. The final element that can be produced by a star really depends on its initial mass. I have an analogy for you to help you understand this. You can compare a star to the game 2048. In this game, there are tiles which are in multiples of 2. You can combine these to double the number of the next tile. The smallest tiles are common and are easy to combine. However, as the game progresses, heavier tiles accumulate and occupy space, making it harder and harder to play. This is comparable to how hydrogen is easily found and combined, while iron and other elements accumulate and just stay there, taking up space. Of course, the analogy isn't perfect, as in the game you can go on combining things indefinitely, but hopefully the point is understood. Stars soon run out of combustible fuel and are stuck with immense forces of gravity and nothing to counteract it. Remember that a star is a system in which gravity is balanced perfectly against the internal pressure generated by nuclear fusion. However, since more and more unfusible heavier elements accumulate, the star generates less pressure to a point where gravity overcomes this force. Here's where things get complicated. Remember that a star is a dynamic system, like a spring. When you apply a force to a spring, it doesn't just stay in place, it pushes back at you. The same applies to a star. When gravity overcomes internal pressure, the star contracts. By contracting, however, the star becomes much hotter, so elements fuse quicker. This generates a huge amount of internal pressure, increasing the rate of nuclear fusion. This makes the internal force generated by fusion overcome gravity, inflating the star out. However, by inflating out, the star becomes cooler, so less elements are fused, and thus gravity pushes it in once again. This cycle of pushing in and pulsing continues for a very long time, each cycle happening faster, until all of the star's fuel is exhausted. It is at this point that the star is in trouble. Only one force dominates: gravity. It has no more fuel for fusion. The star begins to collapse in on itself. This collapse is so powerful and destructive that one would expect all the matter in the star to collapse into itself and form a black hole. This is why I called a star a ticking time bomb. At the end of most star lifetimes, gravity is the only force dominating. So one would expect most stars like the Sun to compress into black holes, right? Wrong. Consider lighter stars which weigh less than 8 solar masses, where one solar mass is equal to the mass of the Sun. When matter is compressed in such small stars, the electrons begin to come closer together. Here, the Pauli Exclusion Principle comes into action. This theory states that no two fermions, or matter particles, can occupy the same position and velocity. If electrons have equal velocities, they must be in a different place in space. If electrons are in the same place, they must have different velocities. This in effect means that two electrons very close to each other will generate a force to keep them from combining. This makes complete sense if you think about it for a second. Since electrons are crushed together in a dying star, They get closer and closer, which means the difference in their velocity is greater and greater. This creates a very, very powerful force known as the electron degeneracy pressure, and it repels gravity and prevents a star from collapsing into a black hole. After all of this has happened, the star is said to have become a white dwarf. In 1919, an Indian scientist, Subramaniam Chandrasekhar, calculated the exact value of this force for stars of varying masses and realized that beyond a certain mass of a white dwarf star of exactly 1.4 solar masses, gravity overcomes the electron degeneracy force. This limit is now known as the Chandrasekhar limit. So, what about stars heavier than this? Surely they become black holes, right? Well, not exactly, because there's another force called the neutron degeneracy force, which in essence is what makes a neutron star what it is. I'll cover these stars in another video. The maximum limit of the mass of a neutron star is called the Volkoff-Oppenheimer limit. However, beyond this limit, there is no force in heavier stars powerful enough to oppose the fierce gravitational compression, and they form black holes. So there you have it. Most stars don't form black holes because of the Pauli exclusion force and to some extent the neutron degeneracy force. Hello everybody, it's been a very long time since I've uploaded and I can explain. I've had the SATs and I've finally gotten that weight off my shoulder so I can upload more frequently. I really hope you enjoyed this video and like it if you do. I've linked all the sources in the description below, so do check that out.